Welcome to qnawire.
All right, let's determine which of these statements is true. I see electrons in first energy level close to nucleus are high energy or highest energy. This seems untrue. False. This is the opposite of what's true. Recall that if we look at, like, I don't know, the Bohr model, and this is our nucleus, and we have these orbitals, that the further the electron gets from the nucleus, the higher the energy it is. That's why, in order for an electron to move from the close energy levels or the first energy levels to maybe like the fifth or the second, a higher energy level, has to absorb a photon, has to get energy, right? That's because to move from a low energy orbital to a high energy orbital, it has to absorb energy. Just maybe a way you can conceptualize that. But that first one is definitely not true about atomic orbitals. An orbital can contain a maximum of 2 electrons. That is true. That comes out of the Pauli exclusion principle. And we recall that any 2 electrons cannot occupy the same energy level, right? And if you're in an orbital, you have the same energy level as other electrons in that orbital, except for the spin component of energy. So any orbital can fit 2 electrons because one can be spin up and one can be spin down. So that's a maximum of 2. Unless there's some other way for them to have different energies other than spin, the most electrons you'll ever be able to fit into any one orbital is going to be 2. Okay, a p orbital is spherical in shape. Oh yeah, this is this second answer was true, or statement was true. A p orbital is spherical in shape. That's false. An s orbital is spherical in shape. P orbitals have that dumbbell or peanut shape as it's described, right? So that's not spherical. Okay. P orbitals are always found in groups of 3. Yeah, that's true, right? Because you basically, if you consider like an XYZ plane, p orbitals orient themselves along these axes, z, x, y. You can have the p orbital that's along the z-axis, a p orbital that's along the y-axis, and a p orbital that's along the x-axis, right? We call those px, py, and pc. Yeah, the p orbitals come in groups of 3. That's also borne out by the periodic table. Um, right? I kind of shrunk the D's a little bit there, but think about, you've got boron, carbon, nitrogen, oxygen, fluorine, and neon, or is it argon? I think it's neon. Um, the filling of the elements into the p block, right? This is the p block. Goes electron by electron, right? So this is like 1 electron in the p orbital, 2 electrons in p orbitals, 3 electrons in p orbitals, 4 electrons in p orbitals in the valence shell, 5, 6. Oh, there's just 5 there. right? And this is like the gradual filling of 1p orbital, 2p orbital, 3p orbital. Not 1p, 2p, 3p, but px, py, pc. That's how these fill in. So that's a little more evidence that p orbitals should be in groups of 3. It's just the fact that there's 6 elements in the p block, or 6 groups in the p block. Okay, an s orbital is lower in energy than a p orbital of the same energy level. That is true. Recall that, if we just compare s orbital to p orbitals, s orbitals are closer to the nucleus, right? An electron in an s orbital is going to spend more time closer to the nucleus than a p orbital, where it can be further outside. And as we recall, electrons closer to the nucleus are lower in energy than electrons further away, right? So this also is borne out in if you look at like Hund's rule and the order that orbitals fill in, it's like 1s, 2p, 2s, and then you've got your 2, 3, 2p, then 3s, and then 3p. You always find that these s orbitals are lower than their corresponding p or d counterparts. And that's about it.